All right, in this video we're just going to talk about momentum and collisions. Biggest thing that we have to know is that momentum is always conserved. No matter what type of collision it is, it's always conserved. There are really two main types of collisions. There are elastic and inelastic collisions. And here you can see elastic collisions, energy is conserved, and inelastic collisions, energy is not conserved. So when a question is posed to you, was the collision elastic or inelastic, you usually have to solve for the initial kinetic energies and see if they equal the final kinetic energies. And if they do, it's elastic. If they don't, it's inelastic. And for momentum is always conserved, we usually start with this just idea that the net momentum before the collision has to equal the net momentum after the collision. And we're going to use an apostrophe, which is actually called a prime, to note final. Because once we have a lot of objects, it's easier to put a prime than to add another subscript. For most collisions, we're going to look at two objects. So in one situation, we can have this object moving towards another object, and then they collide, and they can end up moving independently of each other. All right, so this would be the bouncy type of collision. So we net up the momentum of the first two objects, so we would take m1 v1 plus m2 v2, whatever those values are, whether it's 0 or moving to the left, which would be negative, and that's the total momentum before the collision, and that has to equal the total momentum after the collision. And again, I think we called this type of situation the bouncy situation last year. Now, we can also have situations where the objects will collide and stick together. That's my symbol for collision. And since they'll be basically coupled together, they'll be moving with the same speed after the collision. So again, net up the momentums of each object, and after the collision, that's the equal sign, and you would end up with really one object of combined mass moving with a certain speed. And what do we call that? We call that the sticky situation. The other one would be an explosion. So we have one object with a total mass of, we'll just say it's m1, m2, not moving. It could be moving. We can give it some speed. And then what happens is it'll explode, and the two pieces would end up moving afterwards. But the same deal. Add up all the momentum before the explosion. So total mass is moving at some speed or not moving at all. And then the sum of the momentums afterwards. Now, if this object was at rest at first, that means that the two momentums on the right-hand side would have to be equal. All right, so this would equal that in that type of stationary explosion. And again, we did call that the exploding scenario. But they all stem from this. It's really just this idea. And when we look down here, at the sticky one, basically we have M1 moving at a speed and M2 moving at a speed. It just so happens that they are the same speed so that you can pull out that velocity. So it's basically just, if we factor that back in, we get this equation. Same thing over here. If we factor that through, or distribute that through, sorry, you end up with what's up in that equation too. So it's really just this idea, but this is the way you really just need to think about it. Add up all the momentums before, set them equal to all of the momentums after. Now, if it's really just a general momentum collision equation, a situation, this is going to handle all those situations. What we need to see that's new, and something new that we didn't do last year, at least I don't think so, is have momentum in two directions. So let's think about playing some pool, and you fire the cue ball to hit another billiard ball that's at rest. Then there is the collision, and then both objects end up going off at an angle. And just like forces, you have to separate them into their x and y components. So you would solve for the net momentum in the x and set it equal to the final, and you would do the same thing in the y. And you're still going to be able to use the same equations from before. You just got to think about it in terms of its components. So for the x direction, mass 1 does have momentum in the x. Mass 2 doesn't have any. And then mass 1 has momentum in the x after the collision, as well does mass 2. And then you would have to do the same thing in the y. No object before the collision is moving up and down. So the starting momentum is 0. And then you just have the two y components added together on the right-hand side. Theta 2. Did it. Close enough. Okay. And once you set that up, just like forces, if you have to set that up, there should be enough information given that you could solve for what you're looking for by combining those equations in some way. And in the y with those components there, that upward component of that momentum and that downward component have to be equal, since that plus that has to equal 0. And of course, they're equal and opposite, so mass 2's final momentum would have to be negative. All right, so this is one type of two-dimensional momentum problem. The other type would be if they are moving at right angles to each other. So here, mass 1 moving this way, and here mass 2 moving this way. And they will combine at some point. Okay. And a lot of times with this, this will be a sticky situation, so that they'll stick together as a combined mass. Think of like a car crash or something. And that'll be moving away at some other final speed. If we set it up the same way, though, that the x momentum has to equal the final x momentum, in this situation, only one of them before the collision is moving left and right, so the total momentum of just the first object has to equal only the x component momentum of that object. So it'll be m1 plus m2 times that final velocity, but the cosine of theta is still there. And the equation in the y, just think about it the same way. Only m2 is moving in the y before the collision. And we only worry about the y component of the momentum after the collision. And that's probably all you're going to see in the two-directional momentum collision problems.